Mars, Jupiter, wherever across the galaxy, and now Alice wants to transmit an unknown quantum state psi over to Bob. Okay? And the problem, of course, is she can't measure psi. As soon as she does, she would collapse it into 0 or 1, and therefore she would not learn enough about the state psi to simply transmit the coefficients alpha and beta to Bob. So she can't just do that. And of course, the no cloning theorem forbids her from simply creating many copies of the state. So what can she do? Okay, so and the idea of this comes from Bennett and Brassard in 1993. And this is a very, very beautiful and nice protocol. Okay, so the key realization that Bennett and Brassard had was that suppose A and B had available a device that could do what we call a remote C0 gate. Okay, so even though Alice and Bob are in different locations, okay, and I'll denote this by some, hypothetical sort of shaded region, because of course they can't do this C0 directly, right? They are not local to each other, right? They are in different locations, so they can't really make this C0 gate. But suppose they could make such a C0 gate, okay? So suppose they could make such a C0 gate, then the starting state, let's say, is psi cross with 0 for A and B, and after the C0 gate, if I write out the equation, it's alpha, so this is alpha 0 plus beta 1 cross 0, right, initially when you started out, and then after the C0, you will get alpha 0 0 plus beta 1 1. Okay? Right? So once they have this remote C0, okay, then what Alice can do, so once they have this remote C0, well, what if she measures, let's say in the 0 or 1 basis, of course she has not gained anything, right? Because once again you will collapse into the state 0 0 or the 1 1. You have not gained any knowledge about the coefficients alpha and beta. But suppose you don't do that, think back to how we did the 1 qubit phase estimation, right? We did not measure in the 0 or 1 basis. Instead, we measured in the 45-degree basis, which in this notation is simply the Hadamard gate operation. Okay? Okay. So if you put in a Hadamard first, now let's look at what happens. Alpha 0 0 plus beta 1 1 Hadamard on the first qubit A, okay, is alpha 0 plus 1 over root 2 times 0 plus beta 0 minus 1 over root 2 times 1. Okay? So if I write that out, I get alpha 0 0 plus alpha 1 0 plus beta 0 1 minus beta 1 1, and outside is 1 over root 2. Now I measure. Okay? So what will happen? Suppose I measure 0. On Alice's qubit. Okay? So suppose Alice measures a 0 on her qubit. Then what happens to the state for Bob? Okay? You get alpha 0b. I'm just putting this b to remind you that when you get the 0 on the first qubit and then 0 on the first qubit, that gives me beta 1 over root 2. Okay, beautiful, right? We just accomplished, and the probability for this to happen, right? Probability is alpha squared over 2 plus beta squared over 2, and if I assume that the initial state was normalized, this is half. Okay? So that's the probability for the 0 on Alice's qubit, right? And this is exactly the state we wanted to transmit. Alpha 0b plus beta 1, right? So we accomplished the goal. But of course, this was probabilistic. What about the other possibility? Measure 1. This is going to happen again with probability half. Well, now I get alpha 0 on the first qubit minus beta 1 on the second qubit. And what do we do now? Straightforward, right? I apply a rotation on Bob, right? Bob still has alpha and beta, just with the wrong sign. And we will know when to apply the gate because we know when we got the 1 on Alice's end. So this we denote by this symbol. Okay? And what gate should I apply to make this go back to alpha 0 plus beta 1? I want to have 0 go to 0 and 1 go to minus 1. Z. Exactly. And that's it. That's the result. So if I had this magic operation, remote C0, okay, then by doing this simple 1 qubit phase estimation combined with a gate that's controlled by a measurement, which we sometimes refer to as a feed forward, or we call that a controlled Z based on measurement, right? So it's just that's just a name for it, right? Then we have accomplished the goal. So measure 1, apply the Z operator, then alpha 0 plus beta 1. And that of course again occurs with probability half. So by using up, if we had this if we had this remote C0 gate, then by making one measurement on A and a text or phone call or a signal, whichever way you want to do it, you can accomplish the goal of quantum teleportation. Remember again, you've destroyed Alice's qubit. So this does not violate no cloning theorem. Okay? At this point, Alice's qubit has collapsed to either 0 or 1, but Bob now has the qubit. Okay? So I'll leave that for a second, and now the question, of course, is, so just remember this, right? We have this circuit in place, and we have achieved the result that Alice indeed has accomplished the goal of sending through the unknown state. So that is just a calculation which shows that this circuit accomplishes the goal. But we don't know how to make this remote C0 gate. However, remember when we started, we said Alice and Bob shared an entangled pair. Okay? And we have not used that entangled pair at all so far. So clearly our goal now must be to see how, if we have an entangled state between two parties, A and B, Alice and Bob, how can we use that to accomplish this goal of a remote C0 operation? Okay? So this is the goal, remote C0. Of course, beyond quantum teleportation, remote C0 is going to be useful for a lot of things in quantum computing. Okay? But let us now consider how to do the remote C0. Okay? I erased all the math because hopefully you can follow it by looking at the circuit. Okay? Alright. So for accomplishing the remote C0, let's start again with the state that Alice is in, which is state psi. And remember now that she also had that entangled pair with Bob. So she had that one qubit which is over here, which is local to her. Right? So that is local to her. So she can do things with that qubit and the unknown quantum state psi. Well, she's got an unknown quantum state, she's got a qubit that's entangled with Bob's qubit, and we know from spooky action at a distance that Einstein famously said about entanglement, right? You know this famous statement, Einstein was very unhappy with entanglement. But let's use that spooky action at a distance. What else can Alice do? Well, obviously she can C naught between these two things, right? Even though she can't do a remote C naught, why doesn't she simply do a local C naught between these two qubits? Okay. So now we have to look at all the possible outcomes of this C naught gate. So let's look at psi times 0, 0, A, 0, 0, which is now, this is 0A, 0B, okay, plus 1A, 1B. Okay, this was the state that we started out in. Okay, so after which I'll write it out. Let's just be careful. And I'm going to use this, we have to be a little bit careful. The first two qubits are Alice's qubits for A, and the last one is Bob's qubit B. Okay, so write it out. Is 0, 0, A, 0, 0, 1 plus no, I made a mistake. Let's see. Let's just alpha 0 plus beta 1. Okay. So that's alpha 0, 0, 0 plus 0, 1, 1 for alpha, right? That one. Plus beta 1, 0, 0 plus beta 1, 1, 1. Okay? All divided by root. Okay, this is the starting state. After I apply C naught, okay, now I get alpha 0, 0, 0 plus alpha 0, 1, 1, because that's with the first qubit is 0, so nothing happens. Beta, now this qubit, because this was 1, this changes to a 1. And this one, the second qubit is a 1, so that changes to a 0. Okay. Okay, now what? Well, we try the same thing. Let's measure now, not the first qubit, because we have to reserve that first qubit, remember, for the end Hadamard measurement, right? So we don't want to destroy that, okay, yet. We don't want to measure that yet, the first qubit. But the second qubit, the one that is the part of the entangled pair, we can certainly measure that, okay? Okay, let's measure it in the logical basis 0. So what happens if you get 0? For the second qubit, let's put that, 2, okay? If I measure this guy and we get a 0, well, there are only two possibilities, right? This is the 0, 0 here, and the state is 1, 1 over here when the second qubit is in the state 0. So we get alpha 0, 0 plus beta 1, 1 divided by root 2. But hey, remember back here, remote C naught? That was exactly the state that the remote C naught needs to prepare. So already we are closer to our goal. If we got a 0 on the second qubit, we have accomplished the goal of the remote C naught. Okay? So, measuring the second guy has already, in the state 0, accomplished the goal of remote C naught. Okay? So we don't have to do anything. But of course, there's other possibility. What happens if we get the state 1? Now we get a different state for the qubit, right? For the qubits that they have. Alpha 0, 1 plus beta 1, 0. That's too bad. We were so close to the remote C naught. Can I fix this? What operator or gate can I apply to the second qubit to fix this? That is Bob's qubit. That's Bob. Not this one. third qubit. That's Bob's qubit. What's the difference between this state and that state? Huh? X? Did you say X? X. Exactly. If I apply the X gate to Bob's qubit, which is the NOT operator, right? X gate, then that's purely to Bob's qubit. I'm not doing anything to Alice. Alpha 0, 0 plus beta 1. So I have a controlled X rotation on Bob's qubit. Just take a little space here. Okay. Which of course is equivalent to C naught, but controlled by a measurement rather than by just a unitary transformation. Okay. At this point, we have accomplished the first part, the remote C naught operation. And therefore, the rest of it just follows. Okay? So the full circuit then is simply take this part, slot it in here, where I did this sort of remote C naught, and then the rest is just what I had already discussed earlier. So we see that this remote C naught, so this is equivalent to A, B, remote C naught. Okay? So this very nice protocol, and now it also allows us to accomplish quantum teleportation, as I just showed you. Now, if we carry out the rest of the circuit, then we have achieved the quantum teleportation, as we already indicated. Okay? So this is a very nice idea by Bennett and Brassard has shown us not only to do quantum teleportation, but also a way to carry out this remote C naught operation. Okay? And this is going to be very important. It is an important protocol in many quantum machines that have been proposed, such as quantum repeaters, distributed quantum computers, and quantum networks, and so on and so forth. Yes?
I'm sorry. So the last step here, it is actually not a
Which one? Sorry?
the remote C naught.
Yes, remote C naught. Yes, this one. Yes.
After we get the measurement result of the second qubit, second qubit, and then we do the X gate on B on the X. So this step is actually not a control X, right? It's just a transfer classical.
Controlled X. This one?
Yeah. This is not a control X, right?
Well, it's controlled by measurement.
Yes. So this measurement result is like we transfer this measurement result.
Yes. So it has to be communicated.
Okay.
Yes.
Okay. So
nothing is going on faster than the speed of light or anything.
Okay.
Yeah, you have to send signals for both. This first operation has to have a classical communication to make sure that you know whether to apply the X operation or not. And so that is going to be one limitation. And then of course, if you want to do the teleportation, you have to do this Hadamard and detection after that again and apply a Z gate again. So that's also a classical communication. So as I said in the beginning of the last lecture, or maybe end of the last lecture, this has also shown that one qubit, right, can only be fully learned or fully accommodated or learned by the combination of an entangled pair plus two classical bits of communication. Okay. So that's we wrote this sort of informal equation. One qubit is equivalent to one entangled pair, which is sometimes referred to as one E bit. Okay. Which really means one entangled pair plus two C bits through quantum teleportation protocol. Okay. And also it means that a qubit is definitely more dense in some sense, has more information in it than just two classical bits. Okay. So that's another interesting sort of, from an information capacity, or people who are very interested in how much better is quantum information than classical information and so on, they are very interested in this kind of questions about, how much information does it take to actually transmit or communicate, what is the information available in a single qubit, and there are more clever schemes for like, demonstrating super dense coding and so on and so forth. Okay? It's called super dense encoding in that sense. This particular statement is called super dense encoding, and it is something that people are still researching about all the kinds of ways in which quantum information is better or has more capacity than classical information. Okay? Okay, so that's the end of the quantum teleportation protocol. As I said, the main thing is to come away from with that is that we are able to also carry out this remote C0 gate as a part of the quantum teleportation protocol, and that is actually turns out to be very useful in many quantum machines such as quantum repeaters and distributed quantum networks and so on. And also I should mention that these experiments have been done. So this is not just something I write down on a blackboard and you forget about it because it's not possible. These are all experiments that have been carried out. For example, originally these experiments were carried out by the groups of Zeilinger and GMY Pan, and they first carried out these experiments obviously first in a laboratory. Then they took the quantum teleportation experiments into between two islands. Then they did it in a city. Then they did, or between two buildings in the city. Then they did it between two islands out in the Pacific Ocean, which had two astronomical telescopes, and they pointed the telescopes at each other, and they used it to like send a signal, like a link between the two parties. And then also now, of course, this quantum teleportation has been carried out from space to the ground between Tibet and the China's Michias satellite, okay, which is also by JMY Pan, led by JMY Pan in Science 2017. So these are well established by now that these things actually work. So Einstein's spooky action at a distance or whatever, he was kind of wrong about not believing it or trusting it. Okay. Okay, so that concludes sort of the what I would say are the simple algorithms to some extent of quantum computing. Now I want to tell you about a real quantum algorithm, which will still be somewhat silly in some sense, but is at least will give us some of the features that we're going to need to understand Shor's algorithm. Okay, which I'm hoping by the end of next week we would have arrived at that situation where we have completed Shor's algorithm. And I don't think I'll have time in this class to discuss other algorithms like Grover's algorithm and so on. Maybe some of that I'll assign as reading, or you can always read it now that you have the basic knowledge. Okay. Okay. So what we're going to do. So I should give a little bit of history, which before we go on, which is that the first algorithm that was published using quantum information or quantum mechanics is actually by Deutsch. Okay. And actually, even before him, Feynman proposed this idea for quantum algorithms. Okay, and he started off on investigating this problem. So Deutsch's problem, which I'll only state because it's you can kind of so I think Feynman in 1982 and Deutsch in 1985 published this algorithm. Okay, and I'm not going to go through the algorithm itself because it's fairly simple. I want to go through Simon's algorithm. Okay, but let me just describe what Deutsch's algorithm was. So in his algorithm, there is a 1-bit input and a 1-bit output. Okay, and there is a function f of x that takes you from the 1-bit to input to the 1-bit output. Remember in the last class when I gave you the general perspective about quantum information, I told you that any function, right, which has some table f of x. So remember the idea was, let's say you have some bit string 000, 001 down to say all the 111. There is 2 to the n of these bit strings, right? And any function f of x which results in some answer, which of course in general could be a complex number, right? is say C0 up to Cn, where n equals 2 to the n, right? This was the general perspective of quantum computing, okay? And I said, this is equivalent, of course, to a unit vector psi equal to summation Ci of x, or of this x, okay? X represents all the bit strings, and in front of each of them I stick the coefficient that corresponds to that particular bit string, 0 up to n, okay? 0 up to n minus 1. Sorry. Okay? And in fact, since Ci is just another name for the value of the function f of x, I can remove this and simply denote everything by x. X goes from 0 up to n minus 1, f of x. Okay? And since there's an f of x there, I may as well just denote the state ket also by that same symbol. So we see that there's a mapping between functions on numbers, right? These binary strings are all numbers from 1 up to n, 0 up to n minus 1, and a state ket, a unit vector in the Hilbert space. Okay. Okay. This was the mental perspective that I reminded you to take, and it's automatically normalized because we demand that every unit vector in the Hilbert space or column vector. This is of course also equivalent to a column vector C0 up to C n minus 1, and we demand that this column vector be normalized, so we don't need anything outside it, because of amplitudes of the probability to be in one of these states must add up to be 1, right? So mod C0 squared plus all the way up to mod Cn minus 1 squared added up together must give me 1. Okay? Alright, now Deutsch's problem is just a much simpler version, 1 bit to 1 bit. Okay? So everything is 2D over here, right? So n equal to 1, so this is a 2 to the 1 dimensional problem going from this side to the right side. Okay? And it turns out then that there are only 4 such functions which we label as f0, f1, f2, f3. Okay? And the inputs, let's say, are x equal to 0 and x equal to 1. I could write it in the same notation, maybe if you want, but I'm writing it slightly different. Like if I were to stick to this notation, there would be a truth table for every one of these functions, right? So f0 would take you from, say, 0 to something, 1 to something, and then f1 would take you, but instead I'm labeling it by the types of functions, and then putting the x equal to 0 and 1 over here. So this is 0, 0, 0, 1, 1, 0, 1, 1. Okay? These are the only 4 possibilities. Okay? In fact, we can draw this also in a sort of graph fashion, which is I put the inputs on the left hand side as 0 and 1, and the right hand side as 0 and 1. Okay, this is the input, this is the output. Then you can immediately show that all of the functions correspond to different paths on this graph. Right? These are the only possible connections on the graph, and therefore you can easily verify for yourself which of these, from going from, say, 0 to 0 and 0 to 1, that is clearly, this is f0 and this is f1 and so on and so forth. Okay, again, as I said, I'm not spending the time on it, but we can now classify the functions as something that we call either constant functions, okay, and those are f0 and f3. And the reason, of course, is that f0 and f3 map the input starting state 0. f0 takes it to 0. If the input starting state is 1, also takes it to 0. So this is constant, right? So f of x or f of 0 is equal to f of 1. Okay? And the balanced functions right? f1 and f2 you can see that f of 0 and is equal to 0, f of 1 is equal to 1, right? Okay, so they're not equal to each other. Okay. Okay. Okay, so this is just a setup of the problem. I'm not going to describe what was actually done by Deutsch, but what he showed was that if you can, is to learn whether f is constant or balanced. That is not to actually learn which function you're using, but whether it belongs in one of these two categories, constant or balanced, with just one query to the quantum circuit that implements this function. So you don't know which function you have, but you are given somebody, this is a sort of so-called black box or oracle type problem. Okay, that if you do any more reading in quantum information, you'll find that this is often the way in which things are stated. Okay, it's a black box or oracle type problems, which is that you're given an implementation, somebody creates a chip, okay, a magic chip, a quantum circuit, okay, which implements the function f, but they don't tell you which one they have implemented. Okay? And what they do is they give you the circuit, and your duty or your job is to figure out which one they have used without querying the chip too many times. How many times can you do it? Classically, you can easily ask yourself this question, it's very obvious, you have to query this chip at least twice. Because you need to learn the value of f0 and f1, both. That's the only way you can know whether they are equal to each other, so you need to query them both, send in 0, send in 1, find the answer, and that's it. And this was all that anyone would think to do, and it's the right way to do it. Okay? So, but because we have learned some quantum, right? As you know, in the last class I talked about quantum parallelism, right? Where I said that if you can prepare the superposition of all the input states, 0, 0, of x, remember, and we know how to do that by applying Hadamard's on all the input qubits, then we can prepare a superposition of all the states and send that into the quantum circuit, and then by a clever measurement technique that Deutsch invented in this algorithm, he can discover whether the function is balanced or constant by just one query to the circuit. Okay? Now this function f doesn't have to be trivial, okay, but I should mention that. Okay, you may say, well, what is so great about this function f? Right? I mean, it looks silly, right? But what if function f, or the circuit that implements function f, for example, is calculating the value of the millionth bit in some expansion of a function that you're trying to evaluate. Let's say it's a function that encodes the special properties of some material, okay? And you want to know the value of the millionth bit in this because that tells you something about the material, okay, that you have created, okay? I'm just giving you some obviously random example, but I'm just saying the function f doesn't have to be simple in some sense. It can be telling you the value of some important bit in some computation. Okay, that's the idea of this f. F need not be a simple function, it could be something very complicated, okay? And the point is that quantum circuit might be very expensive and you don't want to query it, and you don't want to use it too many times. Maybe the quantum circuit lives in Mars or Jupiter and it's creating some new computation and you don't want to be able to destroy that, etc. Okay, these are all obviously very made up examples, nothing that's going to happen right away, but the point is to understand the power of this. And what Deutsch's algorithm, okay, so Deutsch's algorithm showed was that you only had to query the circuit one time, okay? And then Deutsch and Joza invented a version of this, okay? So Joza came along, where they extended this to many bits. Okay, they showed that it doesn't just have to be functions that take one bit to one bit. It can be several bits to several bits, m bits to m bits, or n bits to m bits, etc. And again, you get a sort of speed up of the number of times that you have to do the algorithm or implement the function f. Now obviously you can think of more complicated functions that could do something like this, so it started to become a little bit more interesting, right? They were coming up with algorithms that are a little bit more interesting to people, okay? But it's still again very, sort of in this picture is very sort of boring to normal applications. And certainly for computational people it was very exciting because they were like, oh, this is a new type of computing that's allowing us to do something that nobody had been able to do before. Okay? But then along came Simon. And once again, the kind of thing that I'm going to tell you in this algorithm is not yet very, very powerful. Okay? So just to, I forget, I should have tried to figure out, but you can look this up, when Deutsch-Jozsa was published. Yeah, I don't know. I didn't look that up. But Simon came along a couple years later. Once again, I forget to look up when exactly he published his paper. But this is the algorithm that we are going to discuss because, as I will show you in a minute, this algorithm is a special case of Shor's algorithm. So by understanding this, we'll be able to generalize it and understand how to do Shor's algorithm, which of course is the one that is the most famous one and the one that has driven a lot of the interest in quantum computing. Okay, so let's get into Simon's algorithm first. And maybe I can assign some parts of the Deutsch-Jozsa algorithm to homework so that you can read up on it. Okay. So in Simon's algorithm, once again, as usual, we are interested in understanding some properties of functions. So that is the big thing that we are learning, right? That this is what quantum computing is good for, is learning some properties of the function without necessarily understanding every value of the function itself. Okay. A lot of times, maybe we don't care about the value of the function, we want to understand some property of the function. Okay? And in Deutsch-Jozsa case, it was whether this function is constant or balanced. In Simon's problem, he considers a function f of x, which is equal to f of y, if and only if x equals y plus a. Okay? So x and y are two binary strings. Okay, and a is something that we call the period of the function. Okay, you can think of this as like, of course, in a mathematical term or a computational term, maybe f is a function like I was just describing, where and of course x is some belonging to 0, 1 to the power n, y belongs to say 0, 1 to the power n. Okay? Remember when we were discussing the sort of general structure of quantum computers, they take you from something like n-bit strings to m-bit strings, for example. Okay? And this y need not just be a string. For example, you could imagine that it encodes some information about something important. Like I was describing to you, maybe it encodes information about material properties, for example, right? Or because this function f is a very complicated function that is, doing this amazing thing, or maybe it encodes, my favorite thing is, say, strings on the guitar, right? Which is my, as I play the guitar. So I like to think about this as, it's reading out some symphony, some amazing symphony that somebody has written, okay? And so all the strings on the guitar, if I knew which one to play at which point and all the notes on the guitar, then of course I have this amazing symphony. So let's say that this is some, music, okay? So I'm just giving that as an example of, different things you could imagine this function f to be doing. It doesn't just have to be computing some mathematical function, okay? Okay, so first let's consider, and of course we want this symphony or this music apparently has some beautiful repetition time, repetition period that we want to understand. But let's just do the simple example. So say n equal to 3, okay, and I'm going to, as I said, denote the notes of this, say n equal to 3, and let's say that the period is, say, 1, 0, 1, okay? Then let's just write out what this function f of x could be doing. So it's 0, 0, 0, and if you know anything about guitar strings, maybe this is the A note on the guitar, This is 0, 0, 1, is say the B note on the guitar, and then 0, 1, 0 is the G string, and then 0, 1, 1 is the D string. And now, as I said that there is a repetition of 1, 0, 1 that that this music is following. So when I add 1, 0, 1 to this 0, 0, 0 or 1, 0, 1 to the 0, 0, 1 string, then I'm going to get back, say, the 1, 0, 0 string is again has to be B. Okay, the note B. Okay, so this is an example, right? So 1, 0, 1 now, of course, is going to be A, and then D, and then G. Okay. All right. So that is just all the notes on the guitar that this function f of x is plucking or is producing. And so this periodicity, as you can see, there is nothing that I can. So normally when we are physicists, we think about periods. We think about some simple function, sine, cosine, etc. But this guy is obviously completely random, right? In some sense, like if you looked at a representation of f in terms of numbers, and of course each of these is represented by some number. In this case, let's say there are A, B, G, D. There are four distinct possibilities in the music. So this is represented by say 0, 0, 0, 1, 1, 0, 1, 1. And then so your function f of x is mapping you from 3 bits to 2 bits. Okay, in this particular case, but it could be more general than this. And so the repetition rate, as you can see here, is not very obvious. So if I denoted 0, 0, 0, 1, 1, 0, 1, 1, and now B is again 0, 1, and then A is again 0, 0, D is again 1, 1, and G is again 1, 0. So if I just were to give you this pattern here of numbers or letters or convert this to decimal, whatever you want, and you were just given this set of patterns. Okay, this set of numbers, and I asked you to find me the periodicity of this pattern, you would have a hard time, right? Unless you knew A equals 1, 0, 1, and that's how this function was behaving, you might have a little. I'm sure after staring at it for a while, you'll figure it out, right? But in general, it's not so easy. Okay. So that is Simon's problem.
Sorry.
Yeah.
I just want to make sure I understand.
Yes, this is the problem, right? I have not said anything about the solution.
Yeah, I'm just trying to understand if I understand all this thing right. So assume this fx is like a black box.
Assume it's a black box.
A circuit.
Yeah, so, some circuit. Yeah.
If I have 3 input bits from the left, if I apply this kind of oracle here, I should have 2 output.
Yeah.
Which is
right.
Okay.
Exactly.
I see.
Yes. I'm getting 2 outputs. Correct. That's okay. We talked about this in the last class. I don't know if you were here. Is that it's okay for that to happen because we can always extend this into the quantum circuit language by constructing a reversible operation that maps one of the input qubits into like an ancilla qubit and so on. I didn't give you all the details, but it's possible to consider those circuits. Okay. All right. So, and so, how would you go about finding the period A with as few calls to f as possible? Okay. Well, it turns out in the classical computing world, again, remember I told you I'm not going to teach you all about how they prove all these results. There's obviously a whole branch of computer science, and they have examined many of these problems to understand the limitations, but the classical best algorithm that anyone has been able to find for this problem is simply to pick different values of the x values. So classical algorithm picks different x0, x1, x2, etc. While being very careful to make sure such that x0 plus x1 plus x2, etc. is not equal to some other xj in this sequence. And the reason for that is, of course, if that was true, then you would have repetition because of the way in which you pick the values of x0. Okay, but pick them such that eventually you find f of xj is equal to some f of xi. So that's basically a search, right? Search through all the values of f. Okay? By carefully picking the inputs. Okay? And then once you find that xj, then immediately you know that must be equal to a plus xi, and then you have your answer. A is equal to xi plus xj. Okay? Okay, so this is the classical algorithm. So you can immediately see how quickly it grows, right? So if you have m values, if you try this m times, if you try m times before getting success, okay? Then at most you have eliminated those values of A which are pairwise additions of all the values that have not worked so far. Right? So let's say you have a list. So far you have not achieved this desired result, f of xj equal to f of xi. Okay? So you have that list, okay, and you have not been able to achieve the success yet. So you have eliminated all those combinations. x2, x0 plus x1, x1 plus x2, x2 plus x3, none of them work. Because remember that when you get the success, that at that point A will be equal to xi plus xj, right? So prior to success, you have eliminated pairwise m values, okay? You have eliminated all the pairs xi, xj out of m, okay? Which of course is just m choose 2. Right? The number of pairs that you can combine of the m values, and that is just m times m minus 1 divided by 2. Okay? The standard combinatorics, which means that this is going to grow since there are. Remember that we started with the number of values is given by the number of values of the bit string, which is 2 to the n. So, if there are at most 2 to the n values, okay, so then m since there are 2 to the n minus 1 values possible, the minus 1 is because I am eliminating the 0, 0, 0. Okay, so 0, 0, 0 is trivial period, so we don't want that. So out of the 2 to the n possibilities, I am eliminating one of them, which is 0, 0, 0. Not allowed. Okay. So in that case, we see that m is on the order of 2 to the n over 2 before success, right? Because this is basically growing as m squared. Okay? Right? So if this goes as m squared, then m should be on the order of square root of the total number of possibilities before I get a success. Okay, this is, if you don't follow the argument, all I want to show you is that your chance of succeeding requires an exponential growth with the number of bits. Okay? This is the important point. Okay? The problem requires an exponential growth, which is very similar to the Shor's algorithm, that it's going to grow exponentially with the number of bits, and therefore it becomes untractable once you select 100 bits or 1000 bits. Let's say we have 1000 bits, then this is going to take you forever to succeed. And what Simon's algorithm shows, so Simon came up with algorithm works in order of n times. So this is what we call the exponential speed up that is possible with quantum computers. Okay? So let's start with, so I'll leave that over there. let's start with how this works. Okay. You remember Simon is the one who came up with the famous sort of pseudocode for all quantum computers. Okay. The way in which he summarized every quantum computer or quantum algorithm so far invented is this notation or this sort of pseudocode, which he says is rotate, compute, rotate. Okay? And of course, exactly how you do these rotations and computations is the trick of all these algorithms. Okay? So in pictures, let me just draw Simon's algorithm. So first, of course, like before, remember I told you all quantum machines are typically going to have this sort of these n bits that you want to calculate. These are the n input bits. Okay? And we are going to have an m output bits. Okay? Or ancilla bits, whatever you want to call them. They are usually discarded at the end of the computation. Okay? And what I do is apply our famous Hadamard to the n, which I discussed in the last class. Okay? So Hadamard to the n is just Hadamard to the n is just apply Hadamard individually to each qubit in this array. Okay. Okay. So what happens to the state of the system after the Hadamard operation? Well, we discussed that in the last class. That gives you the uniform superposition. So Hadamard acting on the states 0 n gives me 1 over square root of n times summation x equal to 0 up to n minus 1 of x n. Okay? Right? X is all of the bit strings, and the Hadamard operator acting on those states 0 n gives me the uniform superposition of all the possible bit strings 0 0 0 0 up to 1 1 1 1. Okay? We discussed that in the last class. And now we apply the computation. Okay? Remember the computation UF, okay, which is over here, implements that quantum circuit that I just described to you. Okay? So UF acting on that register on this state over here, UF acting on H M0 n, okay? Remember the action of UF, which is the function on any one of these bit strings, produces now the state. So UF acting on the state x n produces the state f of x n, where f of x n is simply, remember, that summation over all the possible again values of x times f of x times x. Okay? And so normally, of course, this would come back on the same input registers, but the idea of this UF or the quantum computer is not to store the results in the original n qubits that were the input qubits, but to store them in these ancilla qubits down here. Especially because we know that the function f of x may not necessarily map n qubits to all the n qubits, but might take you from n qubits to n qubits. Okay? So I'm erasing this part. And these are now in the state. So the total state of the system is 1 over square root of n times summation x equal to 0 up to n minus 1, state x on n, state f of x on m. Okay? Again, you want to write state f of x on m. Maybe I use a different symbol because these are, I already used up x over here, so let me call that y equal to 0 up to 2 to the m minus 1, let me call that capital M minus 1, okay, of f of x, f of y, f of x times y. Okay, y is just a dummy index, right, which stands for all the bit strings between 0, 0, 0 up to 2 to the m minus 1, where 2 to the m minus 1 is, it's like this on this side, over here, right? So the output qubits, right, the outputs A, B, G, D were labeled by bits 0, 0, 0, 1, 1, 0, 1, 1, and this guy will give me the value of the function x multiplied by the state ket 0, 0, 0, 1, 1, 0, 1, 1. Is that clear to everyone this step? Stop me if not. If you see some puzzle look here.
So after the x times xn times fxn, this
Yeah.
is the back to the tensor product.
Yeah. This is the ancilla or output register or whatever, you can give them different names, okay? And last class what we discussed was any classical circuit, okay, can be implemented by an equivalent quantum circuit. So suddenly every classical computation can be accomplished by an equivalent quantum circuit which accomplishes this particular operation. Because we have to make it reversible, that's why we have the extra bits. Because if we didn't have these extra bits, then because remember that the f of x may map you from say 3 qubits to 2 qubits, you would lose one of the qubits, then the operation would no longer be unitary and you would destroy sort of the state of the quantum computer. Okay? So to keep everything unitary, we add extra qubits and we map the answer onto these output or ancilla registers. Is that clear to everyone? It's not, again, as I said, in the notes I've said you can look up the reading in Mermin and in Nielsen and Chuang about how these quantum circuits could be implemented for, and maybe, I can give a little notes or something about how do you implement, say, AND gate, how do you implement, fan out, or how do you implement NOT gate, etc. using a quantum circuit, okay? It's not very difficult, but you can read it or I can give some notes. Yes? No, you ask as many questions as possible.
So before UF, all the
yes.
all the ancilla qubit should be 0.
Still state 0. Correct.
Still 0.
Yes.
And
sorry. So right here, step 1, let's say, or say this is step 1, this is step 2, this is step 3.
So,
and I'm writing here what is at step 3.
Okay.
And at step 2, I wrote it previously. Step 2, the state is summation x equal to 0 n minus 1 x n 0 n.
Okay.
Yes? Are you okay with this? Any questions?
Yes, and then you will apply the UF here.
Yes.
You actually transfer all the xn to the.
Well, xn remains as it is, right? These guys have not changed.
Yeah,
right?
but
f of x has mapped the appropriate values of f of x onto the answer qubits, while the input qubits have remained unchanged. It is always possible in every quantum computation to do this.
Okay.
Even if I gave you a circuit that looks like it destroys some of the qubits, I can build another quantum circuit that uses an ancilla qubit so that the input essentially is control NOT. Okay? If you want, you can look at it that way. Basically what you do is you apply control NOT. Suppose you had a UF which destroys or measures one of the qubits. Then by using a control NOT, you can make sure that the first qubit does not get changed and all the answers get mapped onto the second qubit. And the second qubit I would call as the ancilla qubit here. Okay.
And you do not need to m equal to n, right?
M does not need to be equal to n.
You can
Because f of x may not necessarily preserve the dimension of the space. That's exactly why I use these. Okay, that's exactly why I use a separate set of qubits. So yeah, so it is true that in any quantum computer, you may require twice as many qubits as you would think naively from. So for an n-bit problem, say Shor's algorithm, let's say 1,000 bits, you would need more than 1,000 bits, 1,000 qubits to factor that 1,000-bit number. You will need at least 2,000 bits. Okay. All right. But again, the assumption here is this is still only twice the number of bits. Okay. Whereas the state space, if you increase the number of bits to 2,000, goes by a factor of 2 to the 1,000. Right. So we have gained that. Okay. So let's proceed with the algorithm. I have 10 more minutes, so let's get through it, and then I can maybe summarize. Rotate, compute, and then I said rotate again. Okay? Well, before we do rotate again, some people are often excited by this superposition here, right? Because you just got, as I was explaining, the values of all the possible values of f of x right here in these m states. So they say, magic, quantum parallelism, I have gained some information, but as we discussed in the last class, if I measure this state 3, over here I will get a collapse. I'll get a collapse where it collapses to say some value x naught and some value f of x naught. Okay? So we don't want to do measurement. Okay? What we want to do, well, let's suppose we did a measurement. Okay, then let's consider that argument. Okay? Now how do I argue this? Let me just okay, let's say I did a measurement on these values. Okay? Over here. Which are in the answer. Okay? So I look at the values which are in the answer qubits. I'm going to collapse the superposition to some particular value of this f of x. Okay? And remember that this f of x repeats, it has a period. Okay? Which means when I get an answer f of x, okay, or f of x naught, let's say the answer is some f of x naught, which is in the output qubits over here. Some pattern comes out, which I will call as f of x naught. Okay? That means correspondingly over here, okay, the state of the computer is in the superposition 1 over root 2 x naught plus x naught plus a. That is up here. Is that clear to everyone? The only way I could have got an f of x naught down here is if the input states is basically entangled with the value of the x naught that produced it. Okay? And there are two values of x naught that produce the same value f of x naught. One is x naught itself, and the other is x naught plus a. Okay? Hope that's clear to everyone. Of course, you could ask, well, what about x naught plus a plus a? That's also some other value, but by the bitwise addition, this is just x naught plus a. So in the end, it still reduces down to this same superposition. Okay, wow, that's interesting. But again, it's random. Okay, x naught is random. If I could somehow, as we discussed last time, clone this state and look at it many copies, then I could maybe measure it. But if I measure this right now, if I measure the input register now, I'll collapse into one of these, which once again is just like the problem of trying to determine which one is the period. I'll get either x naught or I'll get x naught plus a, but the random value of x naught is in there, so I can't get a out. Each time I measure, I'll get a different random string which will not tell me enough about the property of A, which is the periodicity that I'm interested in. Okay, and this is where the Simon's original argument, which is rotate again. Okay, we want to rotate again. Where do we want to rotate? Remember, this guy has already been measured out. Okay, the answer register, which contains the values of f of x naught, has been measured out. There's nothing more I can do with that. The interesting thing is here, which is in the values of x naught and x naught plus a. That is the one that has the interesting information about the value of a. So clearly I must rotate here. Okay? So can I erase this because I want to continue this circuit over here. Just remember that part over there. The answer is 1 over root 2 x naught plus then x naught plus a. And to follow the Simon's directive, his pseudocode, which is I'm going to rotate this guy, and of course in quantum computing, rotate means Hadamard again. So this was point 3, which I said at point 3 the state of the qubit is now collapsed to the state x naught plus a after the measurement. Actually, let's do one more. So I'll call, this is time step 3. That is when I wrote down the state, which was summation over x and f of x. Okay? That is, 3 was that point. 4 is after the detection. 4 is over. Okay? And at this point, as I mentioned, I have the values of f of x naught, and over here is the state 1 over root 2 of x plus f of x naught. X naught plus x naught plus a. That is the state 4. Okay? And this is when I apply the Hadamard operation. Okay? Okay, very nice. What does this buy us? Okay? Well, let's look at the action of Hadamard, first of all, on x. Okay? What does that do? Okay? Well, we can write it out, right? Obviously. But let's remind ourselves that Hadamard acting on 0, state 0, gives me state plus. Hadamard acting on 1 gives me state minus. Okay? Which is, of course, the state plus is 0 plus 1 over root 2, and minus is 0 minus 1 over root 2. Okay? So let's say I took a 2-bit string, h, acting on say 0, 0. Okay? Just to give a simple example, right? Then this will produce the state plus plus, right? By this formula, which if I write it out is 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. Okay? 1 over root. Okay? 1 over 2. Clear? Everyone? Right? Just writing it down. You can see that the minus sign over here is the only thing that prevents this from being the uniform superposition. Okay? Right? Oh, sorry. This is the uniform superposition. Right? Because this is plus and plus. So this is just pluses everywhere. Let's take another one. Okay? Obviously, you can see where I was going. This is actually, let's say, the state 0, 1. Okay? Then this is plus times minus. Okay? When it's plus times minus, then you get 0, 0, okay? Minus 0, 1. Plus 1 0 minus 1 1. Right? So we can think of this as saying that it's basically you put a minus sign whenever the sum of these two turns out to be 1. Right? So this is equivalent to 1 over root 2. Okay? Forget the normalization just for a second. This is the equivalent to sum minus 1 to sum over xi of the x. Okay, where xi are the each individual bits. Sum over xi is, of course, that is equal to. Okay, let me back up a little. Right. Let's start again. Let's look at the 1 bit case. Okay, I said that for the 1 bit case, 0 is equal to 0 plus 1 over 2, and h of 1 is 0 minus 1 over 2. Okay, both of these can be written as 0 plus minus 1 to the power of x 1 divided by root 2, where x denotes this input x. Okay? So h acting on a 1 qubit state, h of x, is 0 plus minus 1 to the power x 1 divided by root 2. Now if it's h to the power n acting on some xn, where x is now has many states, so h to the power n times x naught up to xn minus 1, right? Then that can be rewritten over here. I write the answer over here as 1 over square root 2 to the n. Okay, summation y n minus 1 equal to 0 up to 1, summation y n minus 1 equal to y n minus 2 equals 0 up to 1, up to summation y0 equal to 0 up to 1, minus 1 to the power x j yj, summation j equal to 0 up to n minus 1 of the states y n minus 1 up to y0. Because of this property that h acting on x is 0 plus minus 1 to the x1, that is equivalent, once I multiply out all the possible terms, right, to putting a minus 1 whenever the sum of these two products is equal to 1. I know, it's a little harder to take at first. You have to maybe stare at it for some time. Right? Maybe if you did 2 of them, it will convince you that it is indeed the case. Which I did earlier, but I didn't. But this is what I can explain to you, that if I do 2 of them, then indeed it comes out to be exactly this function over here. Let's see if I can rewrite that for you. Right. I had a nice sort of explanation for this written down, which will make it a little easier to take. But I don't see it here, but I'll come back to it. But this is definitely the proof, right? So if I write it in this form and multiply two of these together, right? Then whenever I get, say, minus 1 to the y0 and minus 1 to the power for the yi, then I'll be getting this the power minus 1. Otherwise, if they are equal, then if say the sum of these two is, say, 0, or if the sum of them is 1, then you'll get so. Anytime you have two bits that are 0, 0, then of course you get 0. And if they are, say, 1 plus 1, that also gives me back 0, and therefore I should put the plus sign over there. So that's basically what it's taking care of. The fact that the plus and minus signs will come about only when you have the pairs either an odd number of these 0 1s or an odd number of these 1 zeros, etc. But whenever you have even number of zeros and even number of 1s, then they will give me back a 0, and then I don't have to put a minus sign in front of it. Okay? So this, so once again, h of x on, say, even the 1 qubit guy can be written as 1 over square root of 2 summation y equal to 0 to 1 minus 1 x dot y 1. This is just for the 1 qubit case again. You know, the same thing that I wrote over here. This is summation of y equal to 0 up to 1. So call y as the dummy index that runs over zeros and ones. Okay, so if I have, you know, the minus 1 to the x came from the input, okay, and the 0 and 1, this comes from sort of, you think of it as the output bits, that is in fact what I'm writing over here. Okay, and then the product of many of these is simply going to be the sum over minus 1 to the power of this sum x dot y. Okay, I think maybe that was the missing link that I forgot to write down on the other side. I just see in my notes. Right? So for 1 qubit, if I can write it like this, then it's true. When I multiply together many qubits, I will just get the sum minus 1 over here. Okay? Again, the sum, this can be written as x dot y, which is equal to sum over j equal to 0, okay, minus 1, x j yj, okay, and that is just this construction where the sum is of course modulo 2, so that is also a given. Okay. Let me stop there because in the next class, well, okay, let me. Yeah, I have to stop. Okay, let me finish here. I'll start here and explain how this can be used in Simon's algorithm to find, just remember this point here. We were at this point, and what we want to do is use this information that we get out here to find out the value of A. The value of A is what we are getting to right now. Okay? Thank you. Yeah.
It's not just.
Oh, okay.
It's the people like it's like remember when we talk about the gamma systems, the three-line system.
Yeah, lambda systems. Yeah.
You mentioned about the last state and right state.
Yeah.
When we try to solve the eigenstate of the Hamiltonian,
yeah.
one of the eigenenergy is 0.
Yes.
It's like some
exactly.
combination of the 1
Correct.
and 2.
That's right.
We call this is a
dark state. Correct.
So what exactly means of like what this dark state means in the Hamiltonian distribution? Like, what we can do with this state?
Sure. I can explain that. If you could somehow prepare that state 0, then it means no matter what the evolution of the system is, because it has no eigenenergy or energy goes to 0, it doesn't evolve, right? It stays in that dark state.
Yes, like even there's no phase change,
Exactly, there's no phase change, nothing. Right. So that's the obvious conclusion from that statement.
Yes.
So the other thing that happens is that you can prepare the system. Let's say, sorry, I had to reconstruct. So here's the system, okay, and you have lasers that are driving both of those transitions, and you get two energy levels, three energy levels. There is 0, there is plus, and minus.
Yeah.
And the idea of 0 is it's some combination of these two ground states.
Yes.
Has nothing of the excited state, whereas plus and minus have some combination of the excited state in it as well.
Yes.
Okay. So I think the evolution goes something like this. As you evolve through the lasers, it'll do something like this.
The vertical axis is the energy, or
Yeah, energy.
so.
And this guy over here is, you know, the either like the time or something like that.
So is this will be a sinusoidal, or we are like up close to?
Well, I think the assumption there was two pulses are sort of coming across each other. The two laser pulses that are being turned on,
Okay.
they are coming through each other like this.
Okay, so
So as time goes on, they reach some maximum and minimum over here.
like for example this bright state,
Yeah.
will the increased energy like absorb more photon in it, or what's going on with why? I'm sorry, I not quite understand why the energy will goes up first.
Because omega is changing. The omega, the Rabi frequency,
Yeah.
it goes from 0 at the beginning. It's slowly getting turned on,
Okay.
the pulse. And then after the pulse is gone, then of course it returns back to the original state.
To the
Where-
plus or to zero.
Where they all are back to the initial starting points.
Okay.
Yeah. Yeah, sorry, not 0, but initial starting point, whatever that
I see. However, the zero state
will remain where it is.
okay.
Right. I can maybe discuss it in more detail either in your with my notes on hand, because I can explain to you exactly how the superposition is created. But essentially the idea is that if I started in 0 on one side, then I think if you have omega 1 on, that takes me into the state 2. Right. And 2. And on the other side, if it's omega 2, let's say, that takes me in the state 1, for example.
Okay.
And so, like when I'm in the state 1, and I start turning on the state omega 2, which omega 2 is here, let's say, this is omega 1. You see that if I started in the state 1 and turned on omega 2, I evolve into the state 0
Okay.
first. So this is the counterintuitive pulse sequence. That is, all of my population is in state 1, but I turn on omega 2 laser first.
Okay.
Okay? And by doing that, I prepare the dark state 0.
Okay.
Okay? And after that, as I turn on omega 1, it will evolve into the population 2. So I get a transfer to the state 2
Okay.
without ever going through the excited state.
Yeah.
Because if you remain in the state 0, which is purely a linear combination of 1 and 2.
So like if I already get to the zero state,
Yeah.
like I just turn off also omega 1.
Yes, you can do that. Right.
It should be like stay at.
It should stay at state 0. Yes. If everything were perfect, there was no decoherence, then of course 0, 1 and 2 will remain exact state.
Thank you. That's another question. Sorry.
Yeah, sure.
It's a pretty fast question. So,
Yeah.
so last homework we asked to calculate the T2 star and T2 things.
Huh?
They asked to calculate the T2 star and T2.
Yeah. You just started. Yes.
Yeah, and the difference is like the long coherence time and the short coherence time.
Yeah.
So in the short
Long correlation time.
sorry,
Yeah.
the long correlation time and the short correlation. So in the short correlation
Can we
time.
maybe leave? I think they have to.
Oh, okay, sorry.
There might be people waiting.
So in the short